Hola, hello. Hi everyone, welcome to the first session of contributed talks of the workshop. We're going to start with David Fernandez, who's going to talk us about whole flying qubits in semiconductor quantum dot arrays. Thank you.
Hello everyone, my name is David Fernandez, and thanks Carlos for the introduction. I'm here to talk about how to use quantum dot arrays to transfer quantum information and sending in a fast and very robust way. So now, to understand the core of this discussion, let's delve into what a spin qubit is. As many of you know, a qubit is just a two-level system encoded in any physical system. So the more natural choice is a spin. So this is the idea given by Daniel Loss and David Vincenzo 25 years ago, and is to encode the qubit in the spin of a confined particle. So to make one qubit gate, we need to perform some operations over the qubit using some electrical magnetic fields. Also, for two qubit gates, just we put two spins close to each other, and due to the change interaction, that we interact making two qubit gates. So to read the spin of the spin of the qubit, we couple them to some reservoirs, changing some microscopic properties of the reservoir, and for example the current of the system. And then we have some insight about the state of the particle. So now let's consider the main problem. For making useful quantum algorithms, we need many qubits. So semiconductor quantum dot arrays are very promising because the scale is very small, like 100 of nanometers. But we have one problem. Due to this small change in the voltage to couple the system to the reservoirs, also change other qubits. So this is a cross-talking effect. And to solve this, we can use some spiral architectures in which we have two main components, the computing node and some links coupling to each other. The computing node is a small 2D array with a lot of quantum dots in which the computations are made and the quantum buses connect to each other. This is very similar to what a classical CPU looks like. That you have a lot of cores in which you do the computations, and to share the information between them, you use some quantum buses or cache memory to connect between each other. So I will focus now in how to implement these quantum buses. Semiconductor linear quantum data arrays with multiple sites have been already implemented in experimental device many years ago. But we need a very fast and very high fidelity quantum state transfer. The protocol is very substantial because, for instance, you can use a conveyor belt in which you have the confinement and you move the confinement of the particle, and then the particle move with the ground state of the system. You can also use what is known as the bucket brigade, in which you put two quantum dots in resonance, the particle will tunnel between each other, put out of resonance, and then go on until the particle goes through the system. Okay. Our main is to move particles, but which is the model that we will be using? I will be using whole spin qubits instead of electrons. The main difference between these two particles is the spinobit interaction. This allows for fast spin control and also simplify the experimental devices. And let me be honest, adding new terms in the Hamiltonian is always very funny. And look what happens there. So in semiconductor quantum data arrays, we have two main spinobit interactions. The Dresselhaus one, which is due to the bulk inversion asymmetry of the crystalline structure, but is fixed at the device growing. Once you grow in your system, the Dresselhaus spinobit coupling is fixed. You cannot move it anymore. But the Rosberg spinobit coupling, which is due to the structural inversion asymmetry, is an asymmetry in the confinement potential. You can put some electric fields modulating the confinement potential and then effectively change the Rosberg spinobit coupling. Which is for silicon and germanium, in which they don't have the spinobit coupling, is the only spinobit interaction. And these are the system in which I will be working on. So the spinobit coupling, what affects that? Okay, if you put two quantum dots nearby, then due to the overlap of the wave functions, the particle can tunnel between one not to the other. But due to the spin flip, you can also have spin flip processes in which a tunnel is followed by a flip of the particle. So here I define the spin-orbit ratio, which is just the ratio between the spin flip and the spin conserving processes. And it will be uniform across all the quantum dots, even if you have different tunneling rates in each of the neighboring dots. The whole spin-orbit ratio is kept constant across the quantum dot array. So the theoretical model is as follows. We have three terms, the tuning and the Zeeman splitting due to some magnetic field. We have also the spin conserving tunneling processes and the spin flip tunneling processes. So we are not only interested in a sequential transfer in which the particle is tunneled from 1 to 2 to 2 to 3 and so on, but we are interested in a long range transfer, that is directly going from 1 to 3 with a minimal population on the middle dots. This is bringing us with the concept of dark states. Dark states is a concept originating from the quantum optics community, in which you have a three-level system in a lambda configuration, in which you have state 1 and 2, that is the first and second and the final states, coupled indirectly to some excited state. And this excited state can leak incorrectly, giving some photons to the environment. But there is some dark state, again, state of the system with zero energy, which only have population in 1 and 2 and no population in the excited state. So you can see some transition between 1 and 2 without seeing this photon. That is dark in the experiment. So in our system, we have also a dark state, putting all the levels in resonance. We have this kind of dark state. So if we start the system with the particle on the left, then we can tune the ratio between tunneling rate between 1 and 2 and 2 and 3 dots. And then we can go from left to right. And also you can see here that the final spin projection of the particle is controlled via the spin interaction. Okay. So how we can move these parameters, this tau 1 and tau 2? Well, the first, the most simple example is just a linear ramp in which you start with T2 up and T1 equals to 0 and then close to each other in a linear ramp. You can also use more involved shapes, for example, this Gaussian shape, which is known as coherent transfer variative passage. However, these two protocols are very slow. It works in some regimes, but they need a derivative passage. So to speed up this process, we use what is known as shortcut erraticity, which is, in fact, we use inverse engineering. When you propose an answer for the wave function, then you introduce this to the Hamiltonian, to the Schrödinger equation, and then you solve the Hamiltonian. It's the other way back to usually solving the Schrödinger equation. And then you obtain this kind of shapes. It's very simple, very smooth, very easy to obtain in any experimental devices. However, this protocol is only working for 3 dots. Can we go to larger arrays? The answer is yes, of course. We can use many dots in which we use tau 1 and tau 2, that is the processes as linear ramp, CTP, or SDA. And in the bulk, we use a common straddling pulse, that is just a Gaussian pulse centered at the middle of the protocol. What this does is hybridize the bulk of the quantum dot array, and if the number of dots in the bulk is odd, then we have now a new zero energy that is coupled to the initial and the final state, and then we can recover long range transfer in larger arrays. So here is just some simulation. This is the time needed for the protocol to obtain a fidelity of 99%. As the number of sites in the chain grows. And we can see here that linear ramps, even if it works very well for very small arrays, grows exponentially, but is not very good. For intermediate states, for intermediate quantum dot arrays, CTP and SDA are the better protocols. Or even, SDA is 1 order of magnitude even faster than CTP. So for the rest of this talk, I will only center on SDA. But let's come back. Changing the parameter of the spin coupling also changes the spin polarization. As we can see here, also change with the different number of sites. So this is very interesting because you can tune whether you transfer your particle conserving the spin or flipping the spin. But we can even take this further. Due to the time reversal symmetry, we can build also another dark state in the system and also a linear combination of these two. And then we can compute analytically the total spin rotation of the system versus the total number of the states of and the spin orbit ratio. And then this can be seen just as a rotation around the y-axis in the Bloch sphere. This is just a sample because moving the electric fields, controlling the Rosberg-Pinobly coupling, also move the rotation axis, so we can build any one qubit quantum gate. But why is this interesting? Well, one possible application is generating entangled pairs between very distant computing nodes. We have the left core and the right core, and we want to obtain an entangled state between the left and the right one. And this is connected via a quantum bus. So we start the quantum bus in some arbitrary state. We go with a long range transfer close to the left one, make a swap gate, and then close to the right one. But we can use these quantum gates in parallel to the transfer to speed up this protocol, because usually what you do is transfer and then apply these two quantum gates. But in this case, the whole process is speed up around 40% because the long range transfer protocols is the total time is very close to the total times of the quantum gates. So with this protocol, we even speed up the generator of entangled pairs. And we also can go even further. I will go very briefly to this. There is always noise in the system, but you can protect it using some dynamical decoherence protocols. Like for instance, the Hahn spin echo, in which you have some fluctuation of the magnetic field, then the qubit is spread out around the equator. So what you do is put a pi half rotation, then the noise applies, then you apply a pi rotation, and the noise gets a minus sig, so you have a refocusing of the spin. So we can implement this, and just for benchmarks, we use a sequential transfer, a direct transfer without any quantum gates, but also we can divide our quantum dot array in these 5 parts, in which you apply the pi half, a very big long range transfer, pi transfer, and pi half. Always transferring the particle. The particle will never stop. So just to simulate the dynamical decoupling, we use some hyperfine simulation, and here are the results. You can see that both the direct transfer and the dynamical decoupling with no noise has very large fidelity, but as we increase the noise of the hyperfine interaction, the dynamical decoupling gets very high robustness against this kind of errors. And also we can compare not only just one settling, but settling up and forward and backward, and we can see that this green line, the dynamical decoupling, protects even more the noise. So applying these quantum gates in parallel to the transfer speed up and also protect the qubit during the transfer. And here is very brief conclusions. That's all. Thank you very much.
Thank you very much, David. We have time for maybe a couple of questions. No? Okay.
Thanks for your talk. So what kind of noise are you mitigating with the dynamical decoupling? Exactly?
Usually you correct a very slow noise, like 1 over f noises. That is a random noise that is constant over the whole process of the
So
transfer.
that will be nuclear spins, for instance.
Yeah, exactly. I have simulated nuclear spins.
But you probably cannot mitigate the voltage fluctuation of the gates.
No,
right?
no, not that one. But you can use more convolved dynamical decoupling scheme like stroboscopic effects or something like that, which you protect rapid oscillation fields errors. Yeah.
Great. We have time for another question.
Are you going to test this on some physical device, or do you foresee some future experiments?
Yeah, this is a very big problem, because usually in experimental device, and I don't know why, they really like linear ramps, even if this is not the best scenario. So first we have to convince the experimentalists to use these other protocols. But yeah, I think that it will work at some point. Yeah.
Okay, thanks.
Okay, so let's thank David again. Okay, so now we move to our next talk. We have Carlos Payá from the Instituto de Ciencias de Materiales de Madrid that will talk us about a phenomenology of Majorana zero modes in full-set hybrid nanowires. Thank you.
Well, hello. Thank you first for having me here. And I'm going to present. Do I have a pointer or something? Okay. 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 Oh, okay. I may need it later. So my talk is about the phenomenology of Majorana zero modes in full cell hybrid nanowires. I'm talking about a device to obtain Majorana modes that can be used to build qubits. Okay, so in this talk, I will present you how to engineer these topologically protected edge states that we call Majorana bound states in this specific scenario of a full shell nanowire. Okay, and then I'll talk a little bit about my recent results that were published a few months ago. Okay, so let's start for the beginners on this on what is a Majorana bound state. For this, I'm going to take a very simple Hamiltonian, like the one I have here. Please look at the picture. The ones interested, look at the Hamiltonian, but the rest of you at the picture. I have a chain of spinless fermions, okay? Easy, that's it. Just with hopping and a pairing, okay? Spinless pairing, very important. I can do the mathematical trick of writing each of these fermion operators in terms of what I call Majorana operators. That is just a decomposition between the real and imaginary part of each of those operators. Okay, but if I write my Hamiltonian using those Majorana operators, I can check if I can tune the system to a situation in which I just remain with this term. The others I can make them go to zero. And for that scenario, look, if you look closely at the Hamiltonian, neither gamma 1a or gamma nb are in the Hamiltonian. Okay, that means they are zero energy modes. This has happened because I have undergone what I call a topological phase transition between a scenario B and a scenario C. In general, well, this means that for the non-topological phase, this is B, the strongest coupling is between the Majoranas. But in the topological phase, the strongest coupling is between the Majorana of one fermion with the Majorana of the other one. Okay, so I have these two Majorana bound states at the edges that are pinned at zero energy. Okay, of course, if I'm not at the precise situations in which these modes are completely decoupled from the Hamiltonian, they can go into the chain. Okay, but more or less they are localized at the edges of the chain. Why are these states interesting? Because they follow non-abelian statistics. They are non-abelian anions. This means the order of the exchange in which I can play with them, if I have 4 of them, is important, is relevant. And this makes them suitable to build qubits. But not only a standard qubit, but a topologically protected qubit. They are protected from the coherence at hardware level, okay, because of this topological phase transition. However, if you have noticed in the Hamiltonian, I need a spinless superconductor. This is something that in nature, unfortunately, I do not have. I do not have P-wave superconductors readily available, at least as far as I know. Maybe someone has discovered them this morning. But it was proposed that if I proximitize a standard S-wave superconductor to helical electrons, okay, they behave effectively as a P-wave superconductor. Then it was also, the way to do this was proposed theoretically in nanowires, okay, in semiconductor nanowires with a strong spin-orbit coupling plus a standard S-wave superconductor such as aluminum or whatever. How does this work? Okay, let's take the nanowire, okay, that's a semiconductor nanowire, okay, with a strong spin-orbit coupling. Then the bands have decoupled and have shifted both in energy and momentum, and each of those bands has one spin, okay? Now I'm going to add a Zeeman field. I'm going to add a magnetic field threading the nanowire. This means that those bands are going to split, okay? And each of them is going to have spin, locked spin. This means that each momentum has a determined, a locked spin, okay? So if I go with my chemical potential to the gap, to that Zeeman gap, to the middle of that Zeeman gap, I'm going to just take one of the bands. And this is what is called a helical band. Band with a spin locking. Okay, this is what I need to proximitize to obtain an effective P-wave superconductor. How do I do this? Okay, I just add in the picture the superconductor and apply the general Pauli of the Jens formalism, and I'm going to obtain a band structure that looks like this with two main gaps that I call delta 1 and delta 2. When delta 1 closes, that is what marks the topological transition, and the Majorana bound states appear at the edges of the nanowire, and that is going to be visible in the local density of states of the edge of the nanowire with a zero bias peak. Okay, this is the most important thing I want you to remind. This has been explored experimentally since the 2010s, when this was proposed. Zero bias peaks were detected in several experiments with this kind of nanowires, and this would be fantastic because you would have the possibility to build a qubit protected from the coherence at our level. However, these models are not as simple as I have pictured them to you. You can also obtain this kind of zero bias peaks with non-topological explanations, mainly because we have to take in account multimode effects. The nanowire is not one-dimensional. We need to take in account the electrostatic environment of the wire, that the superconductor renormalizes the parameters of the semiconductor, that we need very high magnetic fields to reach the topological transition in general in these wires. We also have to take in account orbital effects, that there are inhomogeneities, disorder, that I can have quantum dots in the junctions, and so many other things. So most of the claims, or all of the claims of having detected a Majorana were unclaimed a few years later, each of them with the discovery of one of these false Majorana effects. So now our proposal. My research, what I've been working on. Okay, I'm working on the full shell nanowire. This means I have a semiconductor that is completely covered by a superconductor. If you have noticed in the previous slide, the semiconductor was only partially covered. What are the advantages in comparison to the previous system? Well, mainly that now it is the orbital effect that drives the topological transition and not the Zeeman effects. This means that I will need far lower magnetic fields. Okay, this is a huge advantage, and that I also have cylindrical symmetry, and thus the system is far easier to understand in a theoretical context. Only one of the angular momentum modes can undergo the topological transitions. The other will lead to other kind of states. So this is the typical band structure of one of these nanowires. Okay, you see each color is an angular momentum mode. Let's explore it closely. Now here at the left, I'm plotting the local density of states at the edge of the nanowire for each of these angular momentum modes. If I undergo the topological transition, that gap at zero momentum is going to close and reopen, and is going to give me a zero bias peak. Okay, that's a signature of the Majorana bound state. What do the other angular momentum modes do? They're going to give me Van Hove peaks. Okay, where the band minima are, I'm going to have a Van Hove peak in the local density of states. If I have and this is usually the scenario, quite a lot angular momentum modes, I'm going to have lots of these Van Hove peaks. And the drawback of all of this is that sometimes, or most of the times, they are going to cross zero energy, and thus are going to render these Majorana bound states topologically unprotected, because now here I have a state towards the Majorana can decay. So I would have Majoranas without topological protection, and thus useless Majoranas. Okay. Before showing you the rest of the plots, here let me make a very small digression about the little Parks effect. I have a doubly connected superconductor. Okay, it's a cylindrical superconductor, and this means it's going to exhibit this little Parks effect. That is nothing more than the modulation of the superconducting gap with the magnetic flux. Okay, this is due basically this is like if you had yeah, this is the Meissner effect, but an incomplete Meissner effect because the superconductor is too thin, and thus the flux that's not quantized, but quasi-quantized. And that's the origin of these lobulations that you can explore if you want in these 60s papers or in ours too. Pretty well explained. I need you to have this in mind because now when I show you these plots of local density of states against the flux, you will see this little Parks modulation that I'm calling here that is shocking when you see it for the first time, but it's pretty basic physics, so not that interesting. What are all these lines? Okay, all those lines that I see there are these Van Hove peaks that I call Caroli-Deyen-Matricon states analogs because of reasons you can read in the paper. And if I have undergone topological transition, these kind of plots that are interesting because this is the thing that experimentalists measure with a DIDB measurement, well, proportional to this. When I have undergone the topological transition, I will have zero bias peaks where the Majoranas are. Okay? This is what I want the experimentalists to look for in full cell wires. Exactly this? Well, no, because this plot here is made using a very simplified model in which I assume all the charge to be concentrated at the interface of the semiconductor and the superconductor. However, this is not far from reality. In a true wire, if I do the electrostatic simulation with the semiconductor and the superconductor, okay, I'm going to have this kind of band bending of the semiconductor conduction band. And thus, if I tune my chemical potential to be here, usually the wave functions, if only one radial mode has entered the systems, are going to look like this. And thus the charge is going to be concentrated not on the interface, of course, but close to the interface. Still, this plot does not look quite a lot like the previous one. But we can do an approximated model that, in principle, this was just a theory model to explain the phenomenology, but then we have discovered it is quite useful, and we have proposed experimentalists to actually build these insulator semiconductor superconductor wires. Why? Because for these systems, it is far more easy to obtain a topological minigap, a topologically protected Majorana. Look here, this I call a topological minigap because it is black. There is no other state towards the Majorana can decay without enough, with just standard noise. Okay. In all the other plots, I had this Majorana completely covered by Carolis crossing that zero bias peak. Okay. In fact, if I show you the topological phase diagram of one of these previous standard systems, against this is the spin orbit coupling, and this is the chemical potential that I put in my model, you would see that all this blue region is a region where a Majorana or where a zero bias peak is exhibited. But only in these yellowish, greenish areas, that Majorana zero mode, that zero bias peak is topologically protected, has a mini gap that separates it from these Caroli-Deyen-Matricon analog states. So just to summarize, in these full shell nanowires, even if they have lots of advantages in comparison towards the previous models for Majorana nanowires, coexist with these other Caroli-Deyen-Matricon analog states, which are non-topological, and we have to take care of this interaction or their interaction in order to obtain truly topologically protected Majoranas. This means that the topological protection is only achieved for small islands in parameter space, but still it is possible in these, what we call tubular core nanowires, insulator semiconductor superconductors, and we propose this as experimental candidate to obtain Majorana zero modes. If we want to build a full wire, that is what has been excited already experimentally, the phenomenology is far more complex because you have to take in account lots of in general, lots of radial modes also, and thus that structure of all the wave function being close to the interface is not true anymore. So Majorana physics in full cell wires is very rich, and for pristine configurations, the tubular core model is the optimal candidate, in our opinion, to obtain topologically protected Majorana zero modes. This is the people involved in this research. Mainly, the leader is Elsa Prada, my thesis supervisor, but also Ramon Aguado, my other thesis supervisor, and Pablo San Jose. And we are currently in close experimental collaboration with people at Niels Bohr Institute in Copenhagen and these other theoreticians. And that has been everything. Thank you.
Thank you very much, Carlos, for your very interesting talk. Do we have any question from the audience?
Thanks for the talk. So the main difference with the standard proposals is that you are breaking time reversal symmetry at the orbital level instead of spin level, right?
No, you are also breaking it at the spin level, just not through the standard Zeeman field mechanism. In fact, what you are doing is inducing an effective Zeeman field through the orbital effect.
Okay, so but the spin, does it play a role here?
Yes, the spin plays a very important role. You need a spin orbit coupling for this to happen.
Okay, do we have another question?
Do you have any idea of how addressable are those parameter islands when you consider the resolution of the experiments?
Can you repeat the question? How?
How addressable are the parameter islands?
To reach them experimentally?
Yeah.
Well, changing the spin orbit coupling, okay, of the system. The system has the spin orbit coupling it has, but you have to build that. You have to change that from the building of the wire. You cannot gate it or tune it or whatever. But still, you can engineer it somehow to have the values you need.
Okay.
Okay, so let's thank Carlos again.
Thank you.
Okay, so our next speaker is Daniel Michel Pino from the Instituto de Ciencias de Materiales, who's going to talk us about minimal key-type transmon qubit based on double quantum dots. So, the stage is yours.
Okay. Hello, everyone. My name is Mitchell, and I am a PhD candidate under the supervision of Ramón Aguado and María José Calderón at ICMM. I want to thank the organizers for allowing me to be here and present our work about minimal key-type transmon qubit based on double quantum dots. Today, I'm going to show it to you some of the main results of our paper, which has been published in PRB this year with the collaboration of Rubén Saoné Souto and Ramón Aguado. This novel hybrid qubit exploits the physics of superconducting qubits together with semiconducting quantum dots in order to achieve a superconducting parity qubit. But first of all, let me introduce two types of qubits that make up the state-of-the-art of quantum computing: superconducting and semiconducting qubits. You can see a big difference between these two images. On the one hand, these two recent papers claim the control of 4 and 6 qubits in silicon-based quantum processors, whereas IBM has single devices with hundreds of superconducting qubits. But the truth is that both proposals have their pros and cons. For example, semiconducting qubits are good for their scalability because they have a small footprint and they are compatible with current industrial processes in silicon chips. But they fail in multi-qubit interactions over extended distances. On the other hand, with superconducting qubits, we can achieve single devices with a large number of qubits, but they have a limited speed of operations, and these qubits are too large. So we could try to put together these two proposals and make a hybrid qubit with the best of both worlds. This is what this work by Marta Pita Vidal did. They experimentally realized a superconducting spin qubit with a single quantum dot embedded in a superconducting circuit or transmon where the qubit states incorporate an extra degree of freedom due to the spin of the quantum dot that can be manipulated by the phase difference between two superconducting segments in a Josephson junction. We take this idea and replace this single quantum dot by a more complicated system, double quantum dot model. This model has been experimentally realized by Tom DeVere and Wang Zhongwan, and their experimental device corresponds to this sketch, which is composed by two quantum dots coupled by a superconductor with two different interactions depending on if we have an even or odd number of electrons in the system or parity. For example, if we have one electron, it can jump from one quantum dot to the other, and thus going from the occupation state 1, 0 to 0, 1. If we instead have 0 or 2 electrons, even parity, a Cooper pair in a superconductor can split into electrons, one in each quantum dot, and going from 0, 0 to 1, 1. This model is the minimal realization of a QTYR chain or topological superconductor. Indeed, it has a sweet spot where both interactions are equal in strength, where the even and odd ground states are degenerate, and there appear zero energy excitations between them. These excitations correspond to Majorana bound states. Majorana excitations can be understood as the splitting of a single electron into halves. We can see here the different couplings between the Majoranas, and when reaching the sweet spot, remember T equal to delta and both chemical potentials being 0, it kills all the couplings except the red one. So these two Majoranas become isolated and they form a single electron together, which is delocalized along the chain. And this non-locality gives us topological protection. Our proposal takes two of these chains and makes a Josephson junction between them, mediated by a weak link and the phase difference between both superconductors. This system can be separated in two independent parity blocks, even and odd, but for making a qubit, we must focus on the two lowest energy states of a given parity, for example, even. These two states can be understood as a pseudo spin, up and down or 0 and 1. And we can also get an effective Josephson potential that collects the dynamics of these two states. The term that couples them depends on the phase difference between the superconductors and the so-called Majorana coupling, as it is mediated by the Majorana excitations living in the junction. To measure this Majorana coupling, the system is embedded in a superconducting transmon circuit whose Hamiltonian depends on a charging energy and a standard Josephson energy, which give us two independent copies of even and odd parity. But also it depends on our effective Josephson potential that mixes even and odd parity. We also perform a microwave spectroscopy that measures the frequency, the transition frequency between qubit states, and in the charging regime, when EC is greater than EJ, we can, the states are parables with well-defined charge and bad-defined phase, and we predict a single electron channeling process by crossing the sweet spot with T from lesser to greater than delta, where the parity of the ground state changes from odd to even. Even more, in the transmon regime, when EJ is greater than EC, we can approximate the qubit states to two couple harmonic oscillator states, and we can also get an analytical expression of the qubit frequency. And here we can see the Majorana coupling. So if we can measure with microwave spectroscopy, which is a circuit QED technique, we can directly extract the Majorana coupling and also some other quantities that are related to the Majorana quality or topological nature of our system in terms of the parameters of the junction. Finally, let me tell you about our ongoing work. First, we are trying to realize this qubit in Germanium heterostructures with whole states physics, together with José Carlos Abadillo and María José Calderón, and also measure thermodynamic functions together with Gigalmir, like Jobs' supercurrent at finite temperature, and also fractional entropy of Majoranas in the context of non-Hermitian open quantum systems. And finally, let me thank my collaborators and also the European Innovation Council, which has granted with a Pathfinder project, and also our institute. Thank you very much.
Thank you very much for the presentation. Do we have any question from the audience? Okay, I have a question myself. Do you have any idea of the experimental implementation of these ideas? How maybe effects of disorder or many system imperfection can affect the transform qubit?
Well, we haven't measured or calculated the different time lifetime for the qubit, but we predict that only I don't know how to say, quasi-particle positioning will be the source of noise, because we have a parity protection and also protection against the chemical potential noise and so on.
Okay, thank you. Do we have any other question? Okay, so if it's not the case, let's thank the speaker again.
Some PowerPoint.
Okay, so let's move on to the next talk of the session. We have Javier Oliva that will talk us about the speed up of the quantum time evolution of spin qubits in double quantum dots. So, whenever you want.
Thank you for the introduction. I'm Javier Oliva, and I will talk about the time evolution of spin qubits in double quantum dots. So, firstly, I will give a small introduction to this topic. Then I will explain double quantum dot devices, their time evolution, and then give some conclusions. So in physics, there are different definitions of how a physical system evolves and which is the path it follows. So for example, from a classical point of view, we can say that the path between 2 points that followed by the light is the one which minimizes the time, which is the Fermat's principle. Another principle in classical mechanics and more modern mechanics is the principle of Ellipse action, which states that the path followed by a massive body is the one which minimizes the action, which is given by this formula. In quantum field theory, we can say that a particle evolves, the path followed by the particle is given by the average of all possible paths weighted by an exponential related with the action. So we have this formula. But when we have a qubit and in a physical device, which is the path or how it evolves over time. So in order to study that, I will introduce give an introduction in qubits in quantum dots. A quantum dot behaves as an artificial atom with an electron. It is like an hydrogen atom where we apply a potential, which behaves as the positive charge of the atom, and we have an electron on it. This is a figure of the system, schematic figure. They are usually done in semiconductors, where we can imagine a semiconductor with a potential where we can confine an electron, and then we can apply a magnetic field in order to split the energies of the up and the down spin states of the electron. So here we have our spin qubit in one quantum dot. So what happens when we go to another system and we try to encode a qubit in a double quantum dot? So there are 6 different states, 3 triplets and 3 singlets. The singlets are associated when the 2 electrons are in the left quantum dot or in the right quantum dot, or each electron is in different quantum dot. And the triplets, which are the quantum states with a symmetric spin wave function. So we can apply 3 different potentials. We can control the potential of the leftist quantum dot, of the right quantum dot, and also the potential of the barrier. And also we can tune the magnetic field in each quantum dot. So we have a lot of parameters to control, which is the possible states of the quantum dot, of the qubit or the double quantum dot system. So the Hamiltonian is this one. Okay, at the end what we have is the energies of each of the possible states and also the transition. For example, there would be jumps from 2 electrons in the left to 2 electrons in the right. And also there are other possible transitions between singlet and triplet controlled by the potentials and the electromagnetic fields and magnetic fields. So, and also there are other effects of the currents like hyperfine interaction, speed orbiting coupling, etc. So in this talk, I will focus in singlet neutral triplet qubits. So what it is done is, okay, if I reduce the probability of the transitions between my singlet T0 to other states, I can isolate that states and encode my qubit in the singlet and triplet, neutral triplet state. So the Hamiltonian is just a 2x2 matrix with a different interaction, which at the end is the exchange interaction between both electrons, each one in one quantum dot. We can control these qubits, so we can do rotations around Z axis just by varying the exchange coupling, and also we can do rotation around a combination of Z and X, because we cannot turn off the exchange interaction in order to keep our qubit. So we can do these operations to our qubit, these gates, among others, but we will focus in these gates. So, which is important here is, okay, I have 2 possible states, and which are a combination of down-up and up-down. So the only possible path from one state to the other is the straight path, from one to the other and a dephasing. So we can control our qubit in this way. The question here is, okay, what happens if I relax my system and I allow my qubit to populate higher energy levels? and I induce it by applying an external magnetic field, for example. So now what we do is, okay, I allowing my qubit state to go from one state to the other, not only for the direct path, but also it can go through the T plus and T minus states. So we are allowing the qubit to, there are more possible paths from one state to the other. So this is the system I am studying. So the most important thing is, okay, when I had my 2x2 matrix, the singlet and triplet were eigenstates of the Hamiltonian, but in this case, they are not. So the singlet and the T0 are a linear combination of the eigenstates of the 4x4 Hamiltonian. Since they are not eigenstates of the Hamiltonian, they will evolve over time. So at the end, the quantum time evolution of these states are given by the Schrödinger equation, and they evolve. So if we look to the singlet state in the system without leakage, we see that, okay, it is an eigenstate, so it will keep constant over time. But in our case, since we are inducing leakage and population of other states, we see a time evolution of the singlet state with some period, and the eigen energy of the qubit have increased. The same happened with the neutral triplet qubit. So the neutral triplet qubit will evolve also over time. So what we can do is, okay, what happens if I try to do a rotation around the z-axis with leakage and without leakage? We see the red line, the red curve, is a rotation between the plus and minus state over time, and we see that, okay, it rotates from plus to minus to plus, etc. But when there is leakage, we observe some kind like an acceleration of the evolution at the price of some decoherence, but here I force it a lot just to check to plot the acceleration of our system. And the same happens with the rotation around X. It is a linear combination. Actually, it is a linear combination of X and Z, but we also observe the acceleration of the rotation. So in order to exemplify what is happening, we can imagine our qubit at time zero. We prepare a singlet state, which is a linear combination of the 4 eigenstates of the Hamiltonian, and we associate like a clock to each evolution. So at time zero, the system is in the singlet state. But if we let it evolve, all the clocks will dephase. There will be a dephase between all the clocks, and my state won't be the singlet. It will be another one. So after some time, we will observe, after some time t, caps t, we will observe that all the clocks will come back more or less to the same position. So we can say that this evolution from the initial point to again the same point is the least common multiply. So we observe, I repeat the same plots. So we observe that my state starts in the singlet state, and after some time it comes back. We can imagine that my state of the qubit is only in the singlet state, then it populates other states, and then it comes back to the original state. So it is like a population of high energy states and then a comeback. And the same happens with the neutral triplet state. So, okay, which is the bound of this evolution? It is bounded by the slowest clock, because until the slowest clock don't do one turn, the system is not able to come back to the initial state. So this lambda is the one which gives the lower bound. So we can see that the time evolution of our qubit is bounded by the slowest state. And this is important because we are able to control the speed of a quantum evolution by controlling the leakage. So if we want to increase the velocity of the evolution of our system, we have to decrease the slowest period, which is given by the eigen energies. Of course, there will be a trade-off between the fidelity and of our gates and evolution and this effect, and the acceleration. But what we want to do is to study the decoherence of the qubit when we induce this leakage and without it, and we expect a trade-off between the acceleration and the decoherence suffered by this population of high energy levels. So thank you for your attention.
Okay, thank you very much, Javier, for the presentation. Do you have any question? Yeah, back there.
Hi, thank you for the talk. I was curious, I didn't get how you incorporate the leakage, because all the Hamiltonians, how you incorporate the leakage?
Okay, the leakage at the end is controlled by an external magnetic field in the x direction, so you can break the symmetry because the singlet T0 qubit is protected because there is a symmetry of the angular momentum, and by applying a magnetic field in the x direction, you can break it and populate that levels.
So you're not considering like coupling to a bath or anything?
At the moment, no. It's just an ideal system.
Is there like some level that is outside your space, and that is what you consider leakage?
Yeah, and you induce a transition between your computational basis and these high energy levels in order to get an acceleration.
Yeah, thank you.
Okay, we have another question here.
So do you have an intuitive explanation to why it accelerates when you incorporate the leakage?
The most easy way to see it is like you are adding a perturbation to your system, so the energies of the quantum states, the qubit computational states, increase, so then they evolve faster. Or you can imagine you have more possible paths, so instead of only have one path, you have 3 possible paths. So you are increasing the probability of going from one point to the other.
Okay, maybe you have time for another question. I have to move because there is a column in the way, so I can see. Okay, maybe I have one myself. Is there a reason to pick to encode the qubit to choose the singlet neutral? I mean, is there a reason to pick that specific encoding and not another one?
There are different encodings, but this one is very good because you protect your qubit from decoherence because the angular momentum of the singlet and neutral T is equal to 0. Mm-hmm. So they don't interact with external fields, with some source of decoherence, and also the transition between that levels to the T plus and T minus is protected because you need to add an angular momentum to your qubit.
Thank you. Okay, so if there is any more questions, okay, so maybe we can move on to the next speaker so we can thank Javier again. Okay, so now we have the last talk of this session. We have Manuel Gallego, who is going to talk us about neural network ansatz, quantum long range and phase transitions. So, whenever you want.
Thank you very much for the introduction. I'm Manuel. I'm going to tell you how to use machine learning techniques to calculate the current state of some quantum many-body systems. First, these ground states are really important in the context of condensed matter systems. And as important as they are so infamously hard to compute. Beyond those exactly solvable, which allow an analytical solution, we have a lot of models that do not. And in order to deal with them, we have to look for different techniques. Brute force diagonalization only works for so little because the Hilbert space of the system grows exponentially with the system size. And so we are forced to resort to numerical techniques in order to at least approximate these ground states. This has been going on for decades, and each new proposal faced its own limitation. Some were limited by the amount of entanglement they could represent, and other ones had more technical issues like the same sign problem in some Monte Carlo schemes. In 2017, Carleo and Troyer proposed the use of neural networks to approximate these ground states, and that's what we applied. How does this work? How does this scheme work? First of all, the neural network here is just the ansatz to the problem, and in the sense that the input are the states of the computational basis, so ones and minus ones are representing the spin in the z-axis, and the outputs are the unnormalized probability amplitudes, so the coefficients of the wave function. In general, we are not able to recover the whole wave function because, again, the Hilbert space grows exponentially with the system size, so we are forced to resort to sampling techniques and, in general, Monte Carlo algorithms to evaluate observables. So this is just an ansatz involved in a quantum Monte Carlo scheme. This is the particular network we are going to use. It's a visual transformer, and I'm not going to explain its technicalities, but rather a motivation for its use in this problem. Transformer came about like a decade ago, and they were firstly proposed in language tasks, in translation problems generally. And they really succeed because they were able to find long-range correlations between the inputs. This was achieved by mainly two processes. First, relief in the computational cost by dividing the input into subsets called tokens and process them independently. But later on, multi-head attention mechanism is applied in order to find correlation between those tokens, not between the full input individual words in the case of language, but between the tokens, which again really alleviates the computational cost. These transformers to cover the wall, they are the machines behind ChatGPT and were quickly adapted to another task, especially to computer vision. Visual transformers, bits from now, were proposed to deal with images. And they did basically the same. They were great in finding long-range correlation between the pixels of an image, this meaning pixels that are far away from each other. So the motivation is that if we replace the pixels of an image with spins or particles, the problem is kind of the same, finding those correlations. And so it's what we did, basically. Okay, now into the physics. We are going to study long-range quantum systems. These are models which present two-body interactions with decay polynomically with the distance. I was going to motivate them by experimental setup, but Daniel Barredo did a very nice talk about it, so I don't have anything to add to that. But this relevance in the experimental setup motivates the finding of numerical techniques for studying these systems. We are particularly going to focus on the same model, as always, in the long-range version. And we have a parameter alpha, which is the exponent at which the interaction decays, which controls the systems. We have two limits from them. In the limits of alpha 0, the interaction does not decay. So we have homogeneous all-to-all, and the mean field approximation is exact. In the other limit, alpha infinity, the interaction decays too quickly, and we only have nearest neighbors interaction. And again, this model is exactly solvable. Then we have two regions. From 0 to alpha MF, we have systems which sometimes are exactly solvable by mean-field techniques, sometimes not, but in general fall in the universality class of mean-field. So the critical exponents will follow those predicted by mean-field. And another sector from alpha star to infinity, again, the universality class of these systems are the same as nearest neighbors. So we are left with an important sector here from alpha ML to alpha star, which of course depends on the particular system, where we have critical exponents which do not follow those of short range. So we have the importance of the long range correlations while maintaining additivity in the system. This makes this particular region hard to access analytically and further motivates a numerical study. And so our results are going to focus here. First, a little disclaimer, the motivation of this study, the goal is not to get the better results, the better critical exponents ever for this model, but rather to propose a generic ansatz that works in the full range of the system. And again, from all alphas, short range to long range, to make it computational economical. So it can be run in commercial GPUs, computers that any group has access to. This is a one-shot study. We did not do any cherry picking or averaging over realization of the system. And with all of this, we still wanted to get good results, good enough at least to study the properties of the system. So with all of this, going into the results, we first present the full phase diagram for the system. Here in the left panel, we are specifically showing the magnetic fluctuations, or the fluctuation of the staggered generalized magnetization. And here, the darker zone represents ordered zones, ferromagnetic ordering and nil or antiferromagnetic ordering. We also saw a reference for the literature of the critical points, the phase transitions, and we can see that our findings agree very well with those in the literature. And in the right-hand panel, we saw these white line cuts in the phase diagram. And the main here thing in the bottom half is a really great convergence of the model. The curves are really smooth, and again, these are one shot, which really further confirms the great convergence of the model. In the upper panel, we have the V-score, which is just a metric to characterize the variation accuracy of the model. 10 to the minus 4 is a very decent score, but what it's important here, we have a couple of curves. Each color represents a system size, the darker the bigger, 50, 100, and 150. And we see that this model do not deteriorate with the system size, which is great in order to study big systems. Next, a key property of this system, it's entanglement, since it's a property that limited previous attempts. And we are able to recover these curves. We got good results qualitatively. We can see an increment of the entanglement is the second range entanglement entropy. We can see an increment of the entanglement in the critical points, which is as expected because volume law entanglement there is predicted. And when we leave the criticality zones, we see that the entanglement converges to one curve independently of the system size. Again, as expected, because we were hoping for an area law there. We still have some fluctuations, some diffusion on the data, which prevents us from obtaining quantitative good results. For example, this volume law should follow a logarithm of the system size dependence, and we are not able to fully recover those. But this could be addressed by averaging over realization of the system or increasing the computational cost as increasing the sampling. But that was not the philosophy of this study. Then we recover the critical exponents. Here, focus, as I mentioned, in alpha 2.5, which is in that important region. And we are able to do that when you need a great precision in the order parameter that characterizes the phase transition. And here we take advantage of how well the bit architecture reproduces the fluctuations of the magnetization. And so we are able to do some finite size analysis and scaling, collapse the curves in order to obtain the critical exponents and the critical points, which are compared with those reported in literature. And again, we see a nice agreement between those. Finally, I wanted to highlight the importance of the attention mechanism and the tokenization on the input. Here we are comparing again with the p-score, that is just the variance of the Hamiltonian, which should be 0 for a true eigen state. But since it's a variational approximation, it is what it is. So the lower the better. And here we see that the bit architecture is able to report consistently good results through all this, the phase diagram of the system, and consistently better than other architectures like restricted Boltzmann machines, which are the ones firstly proposed in this context of neural network states. Importantly enough, the bit architectures has less parameter than every single RVM here, so and still performs well better. So this highlights the importance and the great design of the bit architecture and how well it is suited for this problem. Well, it's acknowledgement to the people I work with in this project, and some summary of the presentation, and the full text is now available. It was published yesterday. So thank you all for your attention.
Thank you very much for the very interesting talk. Do we have questions from the audience? Two more here.
Yes.
Okay, sorry.
Thank you for your talk. So I got curious about the definition of the bit network. So it's more a geometrical definition through connectivity, kind of a small world network, or it's more dynamical through, it depends on the particular degrees of freedom and strength of the coupling.
Yes, I will say so. I think it's more about the process, the inside processes. The input is that happens to the input, the different first the tokenization, this an embedding, then the multi-head attention, and lastly a post process of the data. I think it's more related. The particular definition of the visual transform is more related to the process that happens inside more than the geometry or anything.
Okay, maybe we have another question.
Hi, thank you very much for your talk. I didn't completely understand. I think you are using quantum data and applying a classical neural network. You are not using a variational form or a quantum neural network, right?
No. The network is completely classical. The whole process is classical, and the data is, at the end of the days, are ones and minus ones.
Yeah.
A set of arrays. So it's quantum data. But
All right. Thank you.
Okay, maybe another question. Okay, maybe I can ask you something. Are there any benchmark of a different neural network architecture for a problem like this?
Yes, actually, yes. There was a paper almost a year ago now that actually used RVMs. Mm-hmm. And for the antiferromagnetic part of this model, so for this part, which is the more complex one, maybe. And they were able to obtain very good results, but the amount of hyperparameter they use, the computational complexity of their model was very hard to reproduce, and we couldn't apply it to the set of GPUs that we have. And so our motivation for this was, okay, do a similar study, but with way less computational power.
I see. And I mean, your system is one-dimensional, right? Do you think that for maybe a two-dimensional model, you could use the same transformer architecture?
Yes, without problem. Yeah.
Very sure about it. Okay. Okay. Last-minute questions. No? Oh, no. Okay. So we are all hungry. Let's have lunch. So thank you. Okay. For having lunch, just as the organizers will guide you. There are like two main cafeterias where you can have lunch. So the organizers will be guiding you for either any one of them. So just seek for us and we will guide you to the cafeteria to have lunch. Thank you very much.
Por supuesto. Vamos a cargarlo.
¿Tenéis un adapter? Es que me lo he dejado, el de USB-C.
Puedo preguntar a... Puedo buscarlo, porque Alejandro tiene uno.
¿Vale?
Sí.
Vale.
Entonces puedo acercarme y... Vale, muy rápido.
¿Tienes un adaptador?
Si no corro al despacho de Alejandro, se lo pido.
Bueno, tampoco hace falta correr, ¿no? Si es a las 2:30 la charla.
Ya, pero lo quiero probar ahora.
Que quiero probar que no nos pase.
¿Qué ha pasado con Daniel? Es que
Yo estaba afuera.
Es que se proyectaba más ancho, han tenido que cambiar, ha sido un poco libre. Tengo algún vídeo y tal.
Sí.
Aparte lo tengo en keynote, tío.
Ya, el que desde luego lo tiene es Alejandro, eso.
Sí.
Usamos el suyo varias veces.
Vale, voy rápido a...
¿Dónde está su despacho?
Yo lo busco, o sea, bueno, es que está en...
Alejandro González.
Sí.
Bueno, yo he quedado con él para comer, le digo
¿Sí?
que venga.
Vale. Bueno.
Quizás lo más fácil.
Sí, quizás más sencillo, porque justo hasta ahora, sí, que todavía no se ha ido a comer. Vale, sí, si quieres dar un toque.
Podemos llamar quizás.
¿Y nadie tiene un
yo creo que...
no, que me lo he olvidado.
Muy bien.
Vale.
Voy a preguntar en conserjería, pero eso es bueno, era el técnico.
Sí.
¿No tendrás un adaptador para probarlo?
Tengo el único coche de mí no tengo. Debe un Roberto.
No.
Bueno.
Vale.
Le llamo.
Igual lo hacemos mejor ahora antes de comer.
Todo, pero abre un email. Bueno,